we're Watford boys, and I'm Neil Nair. We're all year 13.
I'm Mara Luca.
I'm Jakob Skop.
I'm Kshitij Tyagi.
I'm Dominic de Jong.
Okay. In the UK, stagnant wages and high costs of living have contributed to the pertinent issues of housing supply and homelessness. We're grateful for being invited from the UK to come and speak on the matter. In part one, we were challenged to create a model that predicts the changes in housing supply in the cities of Manchester and Brighton over the next 10, 20, and 50 years.
Our first assumption is that in order to forecast the growth of each house type, the only parameter we need is time.
Secondly, we assume no major changes in housing laws are made in the UK over the time frame considered. It is unfeasible to predict such significant legislation on this front.
Finally, to clean the data, we deem the contribution of certain features, such as the caravan type, to be negligible when considering their relatively low proportions.
Initially, we plotted the graph of housing units against time. Noticing a fairly linear trend, we plotted the line of best fit. This was done by minimizing the sum of squared residuals represented by the purple square.
Despite the model fitting the data quite well, when we examined the error against time, we noticed that the model exhibited a trait known as heteroskedasticity. This is a trait where the variance of the error is non-uniform, and its presence in our model suggests that the model may be inadequate at explaining the trend. Instead of this, we decided to consider a logistic regression of each individual house type.
The logistic model, like housing supply, grows rapidly due to increasing demand, reaching a maximum growth rate at T0, before plateauing and reaching a carrying capacity of L due to factors like limited resources. This trend was observed in each of the house types for the UK. In our model, our point of inflection occurs before the time frame considered. This is because the UK is a developed country, hence the plateauing. The exception to this trend was in the house type for flats in the Brighton data. Noticing a change in trend from the 2003 point, we researched further and found that significant legislation favoring the construction of house type, the flat house type over other house types, was implemented in Brighton in 2003. Hence, the data points from before then held little predictive power, justifying their exclusion from our model. Similar trends were seen in 2009 in Manchester and warranted the same adjustment.
We then summed each of the features' logistic equations to get the total housing units as a function of time. The yearly increasing housing supply is defined as the net additions to dwelling statistics per year, according to the UK government. To obtain this, we subtracted the total housing units in the previous year from that in the current, and that's represented by the formula shown here. Our models indicated that in both Brighton and in Manchester, there were a greater number of new accommodations being constructed than decommissioned. In Brighton, however, this trend diminished over time, whereas the opposite was observed in Manchester. This may potentially be due to Manchester's larger size and higher growth rates due to factors such as immigration. Sensitivity analysis was done by scaling each data point by a normally distributed factor lambda, such that the mean is 1 and the variance is 0.05. The model was then retrained on this artificial data 100 times, and a 95% confidence interval was plotted. Across the 50-year time spans that we were considering, the average percentage uncertainty remains under 7% for Brighton and under 15% for Manchester. Very reasonable, especially when considering Manchester's upwards trajectory. This demonstrates that our models are both flexible and are robust.
So onto the advantages of our model. The discontinuity in our function adds to its realism. In reality, no growth model is purely logistic by nature, and random events like government legislation must be accounted for. Another touch of realism is the growth cap in each of our features. This makes our model more suited to extensive feature extrapolation.
However, defining a piecewise function for flats can be seen as overfitting the data in the absence of real-world context. We aim to disprove this via our sensitivity analysis. Finally, over long enough time spans, new government legislation will be implemented, and that may inhibit the growth trends that we've seen, violating our assumptions.
So for part two, we were tasked with predicting changes in homelessness in our two British cities of Brighton and Manchester for the next 10, 20, and 50 years. Starting with the model development, we begin by defining our variables. We use 4 predictive variables of housing units, bottom 20th percentile income, average social rent, and total population of the two cities. And we combine these together using a Bayesian ridge regression. This is very similar to linear regression in that the dependent variable, homelessness, is a linear combination of our 4 predictive variables. However, it does differ in one key area, which is that of the loss function. Although the first term is the same as that in a basic linear regression, there is an additional term which sums the square coefficients of our model. This is because of the problem of collinearity, which often arises when you have highly correlated variables. In a basic linear regression, one might expect the variable, the highest predictive power, which in our case is most likely population, will be used by the linear regression, and other variables will just have very low weights. This leads to very high variance, which is mitigated by this additional term. We then extrapolate each of our predictive variables with time, and using those estimates, we then combine it to get a final prediction for homelessness 50 years from now. One of the assumptions with this model that you can see straight away is that other than housing supply, which we used from our previous question, all the other predictive variables are extrapolated linearly with time. The reason for this is to do with the lack of data, which necessitated us using a more simple model as compared to a more complex one, because that could lead to overfitting and other problems such as that. We also used proxy variables in our measurements. We wanted to use public social rent as our variable. However, we settled on a private social rent because we were not able to find data for that particular variable. We did this with a couple of other variables as well.
Detecting and removing anomalies is a key part to our approach. Initially plotting the data, we thought we saw an anomaly in 2008. So as a result, we decided to quantitatively test this with a semi-custom model. The first step is to set up a power transform. What this does is it normalizes the data to improve the validity of statistical measures of association in the following steps. Then we set up an isolation forest, which recursively eliminates data points with random binary decision trees whose thresholds are set by the contamination variable, which is an assumption of how many outliers are in the data. Then the path lengths for all of the estimators are averaged, and the shorter the path length, the more likely a data point is to be an anomaly. Then we repeat over all the values of contamination. These range from 0 to 1/4. We then retrain the isolation forest, find new outliers, and retrain the ridge regression, calculating a loss on the validation error. Use the median absolute error to eliminate skew from difficult to predict data points, which may themselves be anomalies. Then we compare this to baseline. Repeat this over 5 folds, where each fold has 1/5 of the data randomly assigned to be validation, where we test on it, and the other 4/5 is training, which is used to create the isolation forest and ridge regressor. Looking at this data, we can see that it's fairly spurious in fold 3, and that's because it had a validation set which was particularly difficult to predict. If we repeated this, it may occur again, or it may not. And we only saw it as statistically significant if all folds agreed that there was a decrease in loss. We only found one anomaly, which was Manchester in 2013, and removing this brought down our loss from 13% to 11.8%, which shows our data is fairly consistent. Then, to go into the benefits and disadvantages, we can see some disadvantages are fairly clear. Number one is the use of proxy variables. This isn't ideal because, for example, social housing works significantly differently in other regions or countries, such as the United States, which loses generality if we were to apply this to other places. Another problem is the high levels of loss, which across both cities averaged 11%. This is because 4 variables cannot accurately predict an issue as complex as homelessness. We would need more variables to do this better. However, one major benefit to the model is the decoupling of the time domain and the homelessness predictions. Because in light of new laws or any other information, we can rapidly swap in a new estimator and find new predictions.
Our results for the 2 towns in the UK report roughly doubling in the homeless population for Brighton and approximately 5 times increase for Manchester from the current figures, with Brighton seeing a constant linear growth rate, whereas Manchester sees a gently increasing growth rate. In order to assess the accuracy of these findings, we decide to apply plus or minus 5% noise to each of the coefficients and then re-extrapolate. With this, we got, for our earliest estimates, the percentage error to be plus or minus 8.5% for the two towns and plus or minus 17% for 2074. Considering the timescales involved, we take this to be a success in establishing the suitability of our model weights.
Moving on to part 3, our idea was to evaluate a number of different strategies on a case-by-case basis. We did consider adding natural disaster to this, but we found that they occur relatively infrequently and with very limited severity in the UK. So overall, we deemed their impact negligible. Initially, we had intended to extend our analysis from part 2 into part 3 as well. However, we re-encountered the recurring issue of collinearity. Our first approach was to select a group of strategies, see how they affected our predictor variables from part 2, before finally assessing the resulting changes in homelessness. However, the problem was that we couldn't vary the predictor variables independently. For instance, increasing housing units increased homelessness due to the high correlation between housing units and population. We demonstrated this collinearity a little bit more formally with the correlation matrix shown here. This is a symmetric matrix whereby each element is the squared value of the correlation coefficient of the variables at the intersection. As you can see, all the values are very high, indicating that we did have high levels of collinearity. This caused us to pivot to a series of smaller and more focused analyses, the first of which is increasing minimum wage.
So starting with the assumptions for this smaller model, we first assumed that people who are working minimum wage and people who are homeless and are working are going to be working minimum wage jobs. We tend to find that this is generally true, and we assume that this is a fairly reasonable assumption to make. Our second assumption is that if you have the means to exit homelessness, that is enough spare income to buy some housing, then you will do so as soon as possible. This is a simplifying assumption in order to make the model a bit easier to work with. Our final assumption is that cost is going to be the limiting factor for our model. Now looking at the model itself, we begin by defining a distribution of frequency density of homeless people against spare income per week. That is income after critical expenses in order to keep the homeless person alive, such as food. We expect this to have a high density around 0, as most homeless people are living day to day, and a decreasing density until you reach a figure of 82.4. This is the average social rent according to UK government statistics. And we assume by our second and third assumption that if you have the means to buy that housing, you will exit the category of homelessness. We then look at the orange area on the graph, which represents the proportion of people who are working minimum wage jobs in this case. And we found from government statistics as well that this is around 23.4%. This leads us to find the values of from 42 to 82 pounds per week as spare income. And then any shifts to this orange area will result in a green area, which represents the amount of people that now have been able to exit homelessness. From this model, we can see that there's going to be a £40 cap increase, after which there is no more utility to increasing minimum wage. And this is roughly equivalent to a £1 increase in the minimum wage per hour, which we think is a feasible number to potentially reach, and it looks to be an easy and cost-effective strategy.
Moving on to our next model, we assume that the limiting factor for social housing occupation is its availability rather than the cost. As such, increasing social rental prices may prompt a reinvestment of the profits into building more social houses, as such decreasing the homeless population. We choose an increase of £240 a year, as that corresponds to roughly less than 2 hours worked at the minimum wage per month in the UK. Choosing a 2-year construction period for social houses, we have the following recurrence relation for the number of houses in future years, where we have the number of houses H in some year n plus 2 is going to be the number of houses in the year prior, Hn plus 1, added to the number of houses in year n, Hn, multiplied by the cost, and divided by the average price of building a new social house, C. In effect, this serves as the revenue-generating social houses. This, while being an exponential stepwise function, can be approximated as a linearly increasing function. And extrapolating it, we get that in 17 years' time, the homeless population will roughly halve. While being good for explainability, it neglects other factors such as upkeep, admin, etc.
Finally, we considered migration, although previously not considered. If we let the area of this unit square represent the proportion of a city, the entire population of a city, then the proportion to the left of this partition represent the proportion which are migrants. We can use statistical considerations to find out the probability that given a person is a migrant, that they will also end up homeless. These proportions in blue represent the probability of someone being homeless, and in different cities, they will have them in different amounts. So, for this, we can deploy Bayes' theorem, and combining our data from Manchester, along with proxy cities, we were able to find the data points for each of these probabilities, and then subbing in the numbers gives us a probability of 0.022. That is to say, 1 in every 44 migrants will be homeless. Now, this could suggest that government improvements to the integration of migrants within cities could reduce homelessness.
One of the advantages to our model is its independence from external factors, establishing a clear causal relationship between the strategies and the decrease in homelessness it causes. However, this simplicity makes it unsuitable for long-term timescales, as it means certain assumptions may be invalid. For part 3, we have used a variety of strategies, and we hope that an array of them will be implemented in future years. And with that, thank you for listening, and all questions are greatly appreciated.
Great, thank you. I'll start with a comment and a question. The comment is just the animations are beautiful. Who did the?
Thank you.
Who did the animations?
All of us.
Oh, really? And what do you do them in?
So we used programming with Manim, which is an animation software designed by Free Blue One Brown, which is a math YouTuber.
Okay.
And yeah.
Well, yeah, really impressive. So I had, for part 1, I had a question. I like the sum of regression models that you did where you like broke out the housing types. I had a little bit of trouble interpreting the results. So you had a table that talked about like the final numbers, which were the quote housing supply. And those numbers looked like, I didn't know how to make sense of them. It said like 67 was the housing supply in Brighton Hove. What is that number 67 concretely? What are the units? What does it represent?
So there are two things that we're considering in the part 1. The first one is housing units, and that's the total number of houses in that city. And the second is housing supply, which is the increase or decrease in the number of housing units, effectively the derivative of the function. Yeah. So these numbers represent the change in housing supply or the increase in houses subtracted by the number of houses being decommissioned. So that's
This is like a change per year, per month, or?
So yeah, this would be the change in housing units from 1 year to the next. This is, according to the UK government, the definition of housing supply, which we took for our approach to this problem.
Okay, this makes sense because the numbers are coming down, which is saying the growth rate is slowing, not that the literal housing supply is going down.
Yeah.
Yeah, okay. Okay, perfect. That answers my question. Yeah. Do you have a question?
Yeah, so also in question 1, the data seems to follow a linear trend, but you're not using a linear model. Could you explain why?
So could we go back to the variance plot? Because upon further investigation, we saw that the variance of the error term was non-uniform, which implied that there could be some underlying factors at play here which have crosstalk between each other. Furthermore, since we had data for each individual house feature, we thought it would be better to incorporate them into a more complicated model than just a reductive univariate time series linear regression.
Okay, thank you.
Animation takes a while.
So when you did the logistic regression on that, how did you estimate the parameters?
We use Python, the SciPy library, and it essentially takes in some kind of function and it optimizes the error term that you want. So for us, we use R², which was shown.
Okay, and then when you did the sensitivity, you jittered all of the data?
Yeah, so we scaled them by a normally distributed factor, so roughly 5% change.
Thank you.
So other than doing more cool animations, right? If you had more time during the challenge, what sort of things would you have liked to have done?
There's 2 things. So this is primarily for question 2. What we would have done is we would have had more predictor variables because as we've shown, 4 variables cannot predict such a complex issue. And another thing we would have done is trained the homelessness prediction on multiple cities, and that would allow us to independently vary the data points to get rid of this correlation. So essentially, if you have 2 cities which are almost identical, but one, for example, has a population that's significantly higher, that would instill in the model that higher population leads to higher or lower homelessness. And that would allow us to have a more complex analysis in question 3.
I'm going to jump in really quickly there as well and say, for our final results in part 2, we saw a 5 times increase in the homeless population in Manchester in 2074. And we don't exactly know whether that's perfectly reasonable. I thought it was a little high. So one approach that we could also take is looking at some of the extrapolations we did over time. I think for population, logistic makes a lot more sense. But because we didn't have the data at the time, we didn't use that. But I think we could have used, for example, cities that are very similar in size to Brighton or similar in its economy, so then try and predict stuff like the carrying capacity for those cities and then use that instead of the linear extrapolation.
And if I can jump in, I'd say for part 3 as well, we'd probably consider a lot more strategies. We still consider like 3, 4, but you could come up with many strategies, and it's like the more the better, really.
And a combination of those strategies into one kind of unified approach, or one bigger strategy would be what we would have opted for.
Great. If you want to follow up, go for it.
No, I'm good. Thank you.
Okay. We'll wrap it there then. Thanks.
Thank you for having us.